Today we're going to be covering fluids. So every time you squeeze an open tube of toothpaste, you're demonstrating something called Pascal's principle, which states that any pressure applied on a fluid is transferred undiminished throughout the fluid. So in other words, here you have a container and there's a certain area. Let's say these two containers are connected and you're applying a force downward. Okay, your pressure is applied downward and it will obviously transfer over this way. As this is being pressed down, this is going to rise up. The liquid will rise up. So the formula that we're using is pressure equals force divided by the area. So here we have these two different containers, so we're setting them equal to each other if we want to figure out the force or the area of one or the other. So just to give an example here, let me go ahead and write down our first example here. Okay. So, and that should be area, but my area, A1, right? Let's go ahead and correct that. Okay, so in this example, we want to plug in our first force and our area. Equals, and then they're giving us our area, right? So we know that because of the units, if it's a Newton, we know it goes on the top. But since it's a meter squared, we know that that's our area. So now all we have to do here is we're going to multiply these two numbers. Let me go ahead and grab a calculator. There we go. We're looking for the force. So we're going to do 55 times 2.4, 132. 0.0015 F2, and then we're going to go ahead and divide. This cancels out, and that's going to give us our new force. That's in newtons. Okay, so this is how we figure out the force that is being applied, the area, and the pressure. Okay, so this is actually our pressure. Okay, and let's go ahead and take a look at the next thing. So we're going to be using these formulas here. And this is not supposed to be a P. It's supposed to be a Greek letter that looks like a P, but it's supposed to stand for the density of something. Okay, here we have height, gravity, we know all that. So if you're going down in water, water has the tendency to push things up. And we're going to talk about that in the next slides. But you're obviously going to feel the pressure on the bottommost part. So in other words, if you were kind of upside down like this, and you were swimming in water as opposed to upright like this, you're obviously going to feel more pressure down here in your ears from the water than up here in your feet, right? Because there's more pressure as you go down, okay? So why does a rock feel lighter in water? That's because of something called buoyancy, buoyant force. And the buoyant force is supposed to be the force that water has on objects. It likes to push things up. So here we're going to try to figure out if these items are going to sink or they're going to float. So the first thing that we're going to do is we're going to figure out the buoyant force of water. So the density of water, which is this P part here, which is not a P, it's supposed to stand for, again, a Greek letter, which is called rho. That is 1,000. They're giving us the volume, which is this. And then there we know gravity. So I'm going to go ahead and multiply my numbers. 1,000 times 0.123 times 10 gives me 4 newtons. Okay, and I'm going to write this up here. That is supposed to be the force that water is exerting upwards. Okay, so it's trying to push everything upwards with this much force. So as a result of that, objects feel lighter. Let's do the, oh, come on. Let's use mouse V, okay, for buoyant force. So now what we need to do is we need to figure out the normal force, which is, well, not the normal force, but we're trying to figure out the weight. We're going to convert this into newtons, okay? So same thing that we've done all year long. We're going to go ahead and write like so, right? The mass times gravity. So in this case, it should be, when we do 3.6 times 10 gives me 36. Okay. We're going to do the same with this one. Mass times gravity. We multiply this and we get 4. And same thing here, mass times gravity, 0.36 times 10. And this gives us 3.6 newtons. Okay, so now what we're doing is we're going to compare this number with this number. So since this number is greater than this one, it's going to overcome the buoyant force. In other words, the object is going to sink. It's going to sink down, okay, because it's too heavy. This one, these two numbers, they are the same. Okay, since those two numbers are the same, our objects are actually going to stay in place. So in other words, it's this one is sinking all the way to the bottom. This one is just going to stay kind of like right in the middle. It's not going to move or anything. It's just going to be floating there. And since this one, which number is bigger, 4 or 3.6? Obviously the 4 is bigger, so it's going to pull everything up. So it's going to make this object float. So it's going to be floating up here, okay? It's going to be floating, okay? So that's what a buoyant force is. It's supposed to push everything up. If it's heavier, it'll sink. If it's equal to it, it'll kind of just float right in the middle. And if it's smaller, then it'll make the object float. So let's do an example here. So it says a block is 0.01 meter cube is submerged in water. The density is that. What is a buoyant force? What is the net force? So we're going to go ahead and figure out all of the variables here that it's asking for us. So we're just going to go ahead and plug in our numbers. So remember, this part right here is supposed to be 1,000. That's the density of water. We'll go over that near the end of the video, and I'll explain where that number is, we get that number from. This is our volume, 0.001. And then, of course, gravity. And when I multiply all of this, now let's multiply it. 1,000 times. Let me try that one. Okay. So we get 1. So here we have that object, and it says that there's the object's there. So the buoyant force on this object is 1 Newton. And so the mass of the object, now notice if they don't give you a mass on this, we can use the force of gravity, which is this part right here, okay, PVG. Same thing as the buoyant force over here on the left, because they are giving us the density, okay? So I'm going to plug that in here for rho, which is P. And the volume is going to be the volume of water and gravity. Oh, we're going to go ahead and multiply that out. Let me erase everything. Okay. So we're going to get a really, really big number. Okay, so some corrections that I want to make here is, let me go ahead and multiply this part right here again. So it's 1,000 times 0.001 times 10 gives me 10. Okay, so something wasn't adding up. So we actually have our buoyant force as 10 newtons. Okay, and here we're not using the density, the 1,000. We are using this part right here, okay, 0.001, the volume. Okay, now if I multiply everything, it should come out. There we go. Okay. So now, is this object going to sink or is it going to float? We are going to look at these two numbers. The buoyant force is making the object push up that much force, and we have this force of gravity pulling it down. So it's obviously going to sink. Now, objects do tend to weigh less when they are in water because of the buoyant force. So since this object weighs 27, but the buoyant force is 10, our object is technically going to weigh 27 minus 10, right, is 17 newtons, okay? So picture yourself carrying your friend on your back here in land, and then when you go in the water, they're going to feel lighter, right? Because the buoyant force of water is going to, it's almost like if you have an invisible person helping you. And so this tells us the new weight of the object. So let's go ahead and take a look at another problem here. Okay, so a common brick is about 1.8 times denser than water. What is the net force on a 0.2 meter cube block of bricks underwater? So the same thing that we're going to do. We're going to try to figure out the brick. Is it going to sink? Is it going to float? What exactly is it going to do? So notice here we normally do mg, mass times gravity, but they're not giving us the mass. So we're actually going to have to do rho v g. Okay, I'm going to rewrite it over here so I have more space. So here they are actually telling us we have, let's see, what do they tell us? Common brick is 1.8 denser. So water, the density of water is 1,000. Okay. And so if the density of water is 1,000 and this brick is 1.8 times denser, it would be 1,800. Right? They're giving us our volume and gravity. So when I multiply my two numbers, I get 3,600. That's supposed to be the weight of the brick, right? It's pulling it down this much, okay? So then that's the question is, well, how much is water, right? So water is 1,000. Our volume, they're giving us our volume, 0.2 times gravity. So we're looking for the buoyant force here. Okay. We're just gonna go ahead and multiply. 2,000. So this is 2,000. That's how much the water is being pulled up. So then how much is the new weight of the block, right? So we just subtract these two, the buoyant force pushing up, the block pushing down, subtract these two numbers, and we should get 1,600 newtons. Okay, that's how much the block is going to weigh. Let's try another example here. So first thing you always want to do is get the buoyant force first. And the buoyant force is very simple to get because it's the density of water is always 1,000. It's just a number you'll have to memorize. They're giving us our volume, which is 0.0165 times gravity. Okay. So we enter this in. And we get 165. So we have a little camera that's submerged in water. It's a little camera. And so the buoyant force is 165 newtons. That's how much the force is being pulled up. And so normally we would do, again, this, mass times gravity. They don't give us a mass. Now notice that's the volume. So if they don't give us that, then we're going to have to resort to PVG or rho VG. This is supposed to stand for rho, Greek letter. They don't give us, they do give us the volume, but they don't give us the density of the object. They actually give us this. So they're saying, you know what? We don't want you to solve this part. We're just going to give you what that is. That just makes our life a lot simpler because now if we want to find out the new weight of the object, we just subtract these two numbers. So 1250 minus 165. And the camera now weighs 1085 when it's submerged in water. Okay. So we're moving on here. Okay, so another example here, canoes have plastic foam mounted under the seats for floating in case the canoe fills with water. What is the minimum volume of foam needed for flotation of a 480 Newton canoe? So for this, we're just plugging in our numbers, right, in our formula. Water is 1,000. They want to know the volume, so we don't know V. And we have all the numbers set. So once you plug in your numbers, that should be simple to do. 1,000 times 10 is 10,000. And we divide. And then we get our volume, which is 0.048. The units for volume are meter cubed. Why is it meter cubed? Because when you have an object and you want to know the stuff inside it, you need the volume, right? you need the length times width times the height. And so there's 3 of them, which is our cubed. Okay. Let's go ahead and continue our journey here. Okay. So we kind of already, talked about this. You can take time to go ahead and read it. But Bernoulli's principle is the next thing that we really want to talk about. You just have to memorize this part right here. So when you have a large opening of, let's say, water or a fluid of some time going through a large pipe, and then all of a sudden it goes through a smaller one. And again, it doesn't have to be like a pipe, like plumbing or anything like that. It can be anything. It can be veins, arteries, and so on. So here, this is supposed to be velocity, okay? Don't confuse it with volume. So as velocity increases, the pressure is going to decrease, okay? So as it's going faster, the pressure is going to decrease, okay? So if you have a garden hose, right? Garden hose, and the water's coming out, if you put your thumb through here, you can make the velocity go faster, right? It can shoot out faster. As the velocity is increasing, the pressure is actually decreasing, and it works on the opposite direction, okay? So if you have the velocity is decreasing, having trouble writing here. It's not letting me. So I promise you I don't have that bad of a handwriting, but it's just not letting me. But as the water is going through here, if it starts slowing down, then the pressure is going to increase, okay? It's going to increase. So that's if it's going backwards, okay? But all you have to memorize, just memorize that. Velocity increases, pressure decreases. If it's the opposite, if velocity decreases, then pressure increases, okay? It's just something that you'll have to memorize. Okay, so let's go ahead and skip to here. So which point has the highest pressure? So pretend that you have a little guy here. Okay, it's underneath water. There's another little guy here. Okay. And you're going to feel the pressure in your ears when you're in water, right? You've gone swimming, you swim 10 feet down, you really feel the pressure, okay? So which point is going to have the highest pressure? They're actually all going to have the same amount of pressure. So why is that? The reason for that is because you want to pretend that you have this little guy here, and let's pretend there was boxes stacked directly above his head. Boxes stacked over here and over here. Now he's only going to feel the pressure of the boxes of these right here stacking directly above him, okay? He's only going to feel that. So these other boxes don't really matter. It's just these, okay? So pressure is just dependent on the point. So in other words, if we look at this picture down here, there's going to be more pressure here in the bottom as opposed to up here, okay? If it was moved over to the side, still doesn't matter. This one's going to have more pressure, okay? In fact, if you have a container and you make little holes on the container, there's liquid on the top, you're going to notice that the little hole on the bottom, it's going to shoot out faster. It'll shoot out faster, followed by this one, followed by this one, okay? Once the water starts going down, this one just has more pressure. So pressure is dependent on height. So instead of PVG, it's PHG. That one also tells us that pressure is equivalent to height. Okay. So let's take a look at this problem now. We want to find out how much water or how much of the object is underneath the water. Okay, so we have our values here. Let's plug in our mass and gravity, right? So our mass is right here, 600. So this is 600 newtons, 6,000 newtons. Okay. So notice up here I have the force of gravity is going to equal the buoyant force because it's floating, okay? So whatever number we get here, which we got, I can just plug it in here for my FB. Okay, and then here we're going to plug in, for rho, we're going to plug in the density of water, which is always 1,000. Again, I will cover why that is later on. We're going to go ahead and multiply and divide. And so we get 0.6 meters cubed. Okay. Now we want to find out, well, how much of this is submerged in water, right? So we're going to use this guy right here, volume, length times width times height. So we have our volume, we just solved that. How much is the length? The length seems to be 2. The width is 1. And we're trying to figure out how much is submerged in water. So we're going to go ahead and multiply, divide, 0.6 divided by 2, and we get 0.3. So that's how much is submerged in water, right? Now, if we wanted to know the total, well, the total is right here, right? That's the total height. If we want to know how much is above the water, then that's simple. We're just getting the height, which is 0.5. That's our height, the total height. And we subtract it from this guy right here. So 0.2 is above water. Above. Okay. Let's try another example. Okay. So here we have our mass, gravity, and we have our force of gravity, which is also our buoyant force, right? So I'm going to plug this in here. Rho, which is the density of water. We're trying to figure out the volume, and we know gravity, right? So very simple. Multiply, divide, and our volume here ends up being 0.01. And again, the unit is meter cubed because there's a length, a width, and a height, which is cubed. Okay. So now we're going to plug this in here. We're trying to figure out how much of it is below water. So we're going to get our length and our width. Three times 4 is 12. Divided by 12. 0.01 divided by 12 gives us, this should be 0.0004 because it's a negative 4 exponent. So we move the decimal to the left 4 times, right? 1, 2, 3, 4. That's where they're getting this 4 from. Negative, you're moving it to the left. So this is actually not an accurate picture according to this, because this is showing how much is underneath water. So it's a more accurate picture would be like the entire cube is almost floating off and almost nothing is underneath. Almost nothing is being submerged because this number is so small, right? So we can assume that it's completely floating, okay? That's how we can figure out how much of the object is floating. So we figured out a couple of things. We figured out how much objects weigh when they're in water, how much, if it's floating, how much of it is not floating. And now we're going to figure out velocity and pressure. So these are the three formulas that you will need to know. Okay. And this pretty much tells us the velocity of a fluid that's passing through, the pressure, and the area. Okay. So there's water that's passing through here and through here. And so we want to figure out how fast it's going, the pressure, all that stuff, okay, by doing these steps, okay? So let's take a look at the first one right here. So our first thing that we need to do is here, this area is, let's say it's 2 meters. It's a pipe that's 2 meters in diameter, okay? And so the halfway mark here, so what's half of 2, right? Half of 2 is 1. Okay. We're going to do the same thing right here. What's half of 1? And half of 1 if it lets me 0.5. Okay. Now notice I wrote H2. That's the height. We want to figure out the pressure. And so if you remember over here, right, of the little guys with the boxes going down, the pressure is related to height. Okay. So that's where I'm getting. So I'm getting the height from there to there. Let's get the height from here to here, okay? And let's call that H1, height 1. And the way we figure that out is, okay, well, from here to here, that's 1. From here to here, that's 1 as well. So 1 plus 1 is 2, right? So this is 1. This is 1. So the total height would be 2 meters, okay? So it's going to be important that we label these as H1, H2, velocity, and so on. And you're going to see that that's going to matter, okay? So now we have actually all we need to solve the problem, because if we just go in order, we should be able to solve this. So here, pi, which we all know is 3.14, our radius is going to be 1. Our radius right here is 1, okay? 1. Same thing here, 3.14. Our radius here, our radius right here was 0.5, right? So now we're going to plug this into our calculator. This is simple because 1 squared is 1. 0.5 squared times 3.14 gives us 0.785. And then our units for area are meter squared. Okay, so this is my A1. Okay, so that's step 1. We figured out the area. And now step 2, we're going to plug in these numbers where they go. 3.14, 0.785. And then the velocity V1, we're actually getting it from here on the top. It says V1 equals 3 meters. So that's how fast the water is flowing out from that part. And we're going to solve for V2. Notice over here, we don't have a V2. So this part right here, this is known as the flow rate. So flow rate is supposed to be when you have, you know, something with a, let's say it has a large opening, there's going to be more water that comes out as opposed to a small opening, right? And we can measure the flow rate by using the area times how fast the water's shooting out, and that'll tell us the flow rate, how much water is flowing out, okay? So we actually set these equal to each other because we're getting the flow rate from here, and we're trying to figure out the flow rate from here, so you set them equal to each other. So all I have to do now is divide. And we're going to solve for our velocity. So I'm going to do 3.14 times 3 divided by 4 times 3 divided by 0.785, and that gives me 12. Okay, so that's how fast the water is flowing. So now we're going to come to this very, very long formula. So notice in this formula, we actually have this part right here, which the rho, the P looking thing, which is the density, it's up here, the density for water. We're just going to plug in numbers here. This step looks very daunting, but it's not. It's actually very simple, and you'll see how simple it is. First thing that I want to do is I want to figure out the pressure, okay? So this, I am going to move it to the other side by making it negative, okay? So in other words, this part right here, I'm going to write it again, okay? Let me write it here, 1/2 rho v squared, v2 squared plus rho GH2. And so this part right here, I'm going to make it negative, okay? So instead of plus, it's going to be minus 1/2. And instead of plus, again, I'm going to make it minus because I'm moving all of that over to the other side. And so now it's just a question of plugging in numbers. So here, the rho, it's up here, right? It's 1,000. So anytime I see that P looking thing, which is rho, I'm going to plug in 1,000. My velocity 2. What is my velocity 2? I just got that. It was 12. Don't forget the squared. Okay, plus rho again, gravity, and our height, h2. h2, it's right here, 0.05, okay? 0.05. 0.5. Okay. Let's continue plugging in numbers. Minus 1/2 rho velocity 1. That's our velocity 1, 3. Don't forget the squared because that's part of the formula. Minus rho gravity and my h1. My h1 is the purple over here. We got the height from there to there. That was 2. Okay. All right, so now we're going to go ahead and let's solve this. Let's break it apart. Let's do this part first, and then this part next, minus this part, minus this part, okay? So well, let's let the calculator do the work. So 12 squared times 1,000 divided by 2. This is 72, right? 1,000 times 10, that's 10,000. Half of 10,000 is 5,000. 3 squared, 3 times 3 is 9, times 1,000 divided by 2 gives us 4,500. And 1,000 times 10, 10,000 times 2. Let's add everything up. 72,000 plus 5,000 minus 4,500 minus 20,000. Gives me 52,500. And we're going to put a PA for Pascal, and that's going to be for our pressure. Okay, that's going to be the pressure at that point over here. Okay, point on the right side. Let's do another example. Okay, so here we have all of our, well, we're going to have to break everything apart, right? So here, the halfway mark, halfway of 20 is 10. That's 10 meters. Halfway of 10 here is 5. So that's going to be my H2 equals 5 meters. Okay. That's my height from there to there. I need the height from here to here. So let's label that from here to here. Well, a little hard to do it with the, oh my gosh, it's hard to do it with the mouse. Okay, so that's going to be my H1. That's my first height. This is my second height. Okay, let's emphasize that little 2 here. That's a 2. Okay, so my height, so I know from here to here that's 10. That goes all the way here, so that's 10. And then this is 10 as well, so this would be 20. Right? So that's 10. And then that's another 10, that's 20. That makes sense. Okay, that's it. We have everything that we need to be able to solve our problem, because now it's just plugging the numbers in the formula. The formulas are laid out very nicely. So here we have pi, my radius, which my radius is 10. Same thing over here, 3.14. And my radius is 5. Okay, so let's go ahead and plug in our numbers. So 10 squared is 100 times 3.14 is 314. Same thing over here, 5 times 5 is 25, 78.5. Okay. We're going to plug in our numbers in our next formula. Our velocity 1 is 1. Our velocity 2 we need to solve. So we're going to have to divide 314 times 1 divided by 78.5. So 314 times 1 is 314 divided by 78.5 gives me 4. So 4 meters per second is my velocity 2. Let's just plug that in here. And now we're going to solve for the pressure at that point. Okay, we're solving the pressure over here. So notice the formula is already done for us. We just moved this part. And notice the formulas, if you see them, sometimes they'll have the pressure, the P1 and P2. I'm crossing those out because they're going to equal out each other. So if we want to figure out the pressure of one of them, that's why we're moving this part to the other side by making it negative. Okay. Since we made this negative, now it's just plugging in our numbers. It's not hard to plug in our numbers. We have 1/2 rho, which is 1,000. Even though it's not here, we're assuming that it's water, so we're going to plug that in. My velocity 2 I just got, that was 4. Okay. Plus rho again, gravity. My height 2. My height 2 is, it's right here, height 2, 5 meters. Minus 1/2 rho velocity 1. It's over here. And I'm color coordinating all this so you can see where I'm getting those numbers. Minus rho gravity. And my height 1. My height 1 is right here in purple, 20. Okay, so now it's the easy part, breaking it apart, plugging in your numbers, and just solving to get our final answer. So 4 squared, 4 times 4 times 1,000, 4 times 4 times 1,000 divided by 2 gives me 8,000. 1,000 times 10, 10,000 times 5. Oh my gosh. So 10,000 times 5 is 50,000. I got the little comma in the wrong spot. 50,000. Looks like 500,000. There we go. 50,000. 1 squared times 1,000, half, 500. 1,000 times 10, 10,000 times 20. 10,000 times 20, 200,000. 200,000. And now we add everything up. 8,000 plus 50,000 minus 500 minus 200,000 gives me 142.5 pascals, which is our pressure. Okay. So keep in mind for tests, you will have to memorize just the formulas as always, because the formulas will show you, as long as you know the formulas, you can plug in the numbers, okay? So now I want to talk about this number right here, the 1,000 for P. Now notice in all the problems that there was the rho P looking thing, right? Right here, 1,000, right? So in a bunch of these problems that we did, P for water, 1,000, where do they get that number, 1,000? So first thing we have to understand is density. So what exactly is density? So Y rho equals 1,000 kilograms meter cubed. So that's the density for water. So what exactly does that even mean? Well, let's look at what density is. Density. Density is actually mass divided by volume. So let's say you have an apple, okay? And the apple weighs 2 grams. And let's say the volume is, I don't know, let's say 3, I'm just making up numbers here, 3 milliliters. So the easiest way to figure out the volume in something is you measure how much water you have, and then when you put the object inside, the water level is going to go up. And so the difference between here and here, that is supposed to be the volume. That's how much space it takes up, okay? So when we divide 2 divided by 3, I get 0.6 grams per milliliter, okay? So that's supposed to be the density of water, okay? Now, I want you to see, like, let's say this, this block that we have, let's say the block was twice as big. And we're going to try to figure out the density, okay? So since it's twice as big, first of all, the density, it's not going to be twice as much. So we're not multiplying 0.66. We're not doing this times 2. And we're saying, oh, the density is 1.32. No, that's not what we're going to do, because if you think about it, the block was originally like this, but now it's 2 times bigger, okay? Since it's twice as big, the mass is not going to be 2 grams. It's going to be 4. It's twice as big, right? The volume also got bigger, right? The length, the width, the height, that got twice as big. So if I divide 4 divided by 6, look at that, I get the same number, okay? What if the block was 10 times as big, right? So the original weight was 2, but it's 10 times as big. So now it weighs 20 grams. The volume increased by 10 as well. So it's no longer 3 milliliters, it's 30 milliliters. If I divide this, we're going to get the same thing, okay? So it doesn't matter how big the object is. The density of the object always stays the same. So then where do they get this number from? 1,000 kilogram meter cube. Well, the density of water, let's change the slide. It's too busy. 1,000. This is the density of water, okay? So if you have 50 mLs of water and you put it on a scale to weigh it, it's going to weigh 50 grams. Okay. If you have 100 mLs of water, 100 mLs of water, and you put it in a scale, it's going to weigh 100 grams. If you have 1,000 mLs, it's going to weigh 1,000 grams, and so on, okay? So when you do the mass divided by the volume, we get 1. When we do the mass divided by the volume, we get 1, okay? When we do the mass divided by the volume of water, we're always going to get 1, okay? So here we're going from grams to kilograms. So all this is actually a conversion, okay? So the density of water is 1 gram per milliliter. They actually convert the 1 to 1,000. So to go from grams to kilograms, you actually have to move the decimal over 3 times, which will actually be this, kilograms. But now you need to go from milliliters to meters cubed. And so a milliliter is very, very tiny, okay? Very, very, very tiny. And so what they're doing is they're saying, okay, well, how many length times width times height in meters, how much is that? So it's going to be a very, very, very small number. It's a meter is, it's about 3 feet, right? But a milliliter is actually, and I mean, if I draw it on here to scale, you're not going to be able to see it, but a milliliter to scale would actually probably be about, oh man, it's a very, very tiny amount, okay? So it's going to be like 0.00000 something meters cubed. Pretty much, guys, what happens is they just converted gram per milliliter to this. It's kind of like when you're going, you're converting from milliliters to gallons. There's a conversion factor. Or if you're going from feet to miles, right? If you're converting stuff, you're going to use conversion factors. You're going to either be dividing by how many feet there are in miles and so on. And so that's what this is, okay? That's why we keep using this for water, which is the density. So just a quick review of what we learned. Density is, again, mass divided by volume. Density of water is 1,000 kilogram meter cubed. You always use that for rho, which is the P looking thing. Water has a buoyant force. Water likes to push stuff up. Gravity likes to push stuff down. Depending on which one of these is greater will determine if the object floats or if it sinks. If it floats and we want to figure out how much of that is floating, then we use this formula, this and this, okay? We plug in our numbers, and in order to determine the velocity and the flow rate and the pressure and all that, we use these 3 steps, okay? And that is just a quick rundown of all the stuff that we need to know for fluids.